So, imagine looking out your window, right? And you see this really cute stray cat. And
Wow.
you decide to bring it inside to be your new pet. You name it, you feed it, you give it this cozy little spot on the rug.
As one does, yeah.
Right. But then, the next morning, you look out your window again, and there are like 100 identical cats just sitting in your yard.
Oh, wow. That
Yeah.
is a lot of cats.
Yeah. So what do you do? Do you bring every single one of them inside? Or, do you kind of have to rethink what you even consider a house pet?
Right.
And the funny thing is, in the early 2000s, astronomers basically looked through their telescopes and realized they had this exact same problem, but, with planets.
That is honestly the perfect way to frame one of the most misunderstood moments in, like, modern science.
Yeah.
Oh, absolutely.
Right.
We are, of course, talking about Pluto because, if you mention in a crowded room that Pluto isn't a planet anymore, someone is going to bristle.
Oh, 100%. People get genuinely mad about it.
They do. It feels like this childhood certainty was just snatched away.
Right.
Or like astronomers were just being arbitrarily mean to this small, distant world.
Right, like they bullied it out of the solar system. But today, we are diving into some really fascinating source material that completely flips that whole narrative.
Yeah, it really does.
So the mission for this deep dive is to basically unlearn that whole idea of a demotion. We're going to explore how Pluto's reclassification is actually, it's a triumphant story.
It really is. It's science working exactly how it should.
Exactly. It's a perfect example of science updating itself when the universe, surprises us. Okay, let's unpack this. We are going to take you on a journey to the very edge of our solar system today.
And we should say, we are going to do this assuming you have zero background in astronomy.
Zero, none required.
Right. We aren't going to use heavy jargon without explaining it. And we're going to take our time to really understand the mechanisms of the cosmos. Because we want to explore not just what happened to Pluto, but, the mechanics of why it happened.
The why is the best part.
Yeah, because the why is where the real magic of the scientific method lies. Science is not, it's not a static list of facts you memorize in the third grade.
Right.
It's an active process of refining our categories based on new data, which sometimes requires us to, abandon our assumptions and look at the cosmos with fresh eyes.
Which brings us to the beginning of the whole mess, because before we can really grasp why Pluto lost its planetary status, we kind of have to rewind, right?
We do.
We need to understand how it got that status in the first place and why it was honestly always a bit of a suspicious fit.
Very suspicious.
So let's go back to 1930, the discovery of Pluto.
Right. So 1930 was a totally different era for astronomy. There were no automated computer-guided telescopes mapping the sky in high definition like we have now.
Yeah, no smartphones to just snap a pic of the sky.
Exactly. So Pluto was discovered by a young American astronomer named Clyde Tombaugh. And the way he found it is it's a testament to human endurance.
Oh my gosh, yes.
He used a device called a blink comparator.
I've read about this process, and the sheer, tediousness of it is staggering.
It's mind-numbing.
Right, because he wasn't just looking through an eyepiece, hoping to spot a new planet. He was taking these massive glass photographic plates of the night sky and capturing the exact same patch of space a few days apart.
Right. And then he would load those two glass plates into the blink comparator. And what the machine would do is rapidly switch the view back and forth between plate A and plate B.
Click, click, click.
Exactly. And the fixed stars, which are, incredibly far away, they wouldn't move at all between the photos. But if there was a planet or an asteroid in our solar system, it would have moved slightly along its orbit during those few days.
Right, so by flicking back and forth, the human brain's motion detection kicks in. Out of thousands of static white dots, one tiny speck would appear to jump or blink back and forth.
That is the precise mechanism. And
Yeah.
Tombaugh spent thousands of hours staring into this machine.
Thousands of hours.
Thousands. Analyzing millions of stars, fighting off severe eye strain. And eventually he finds a dot that jumps.
Wow.
And it is immediately hailed as the ninth planet, the supposed planet X that older astronomers had been predicting for years.
But wait, if we are looking closely at the data from day one, Pluto was always an oddball. It never really fit the profile of a major planet.
No, it didn't.
For starters, the size. We eventually realized Pluto is incredibly small. It's smaller than our own moon.
Yes.
It's wild to think about a planet being smaller than the rock orbiting our own planet.
Yeah, size was definitely the first red flag. The early astronomers, they assumed they were looking for a massive gas giant, something that was actively tugging on the orbits of Uranus and Neptune.
Right, because they thought some gravity was messing with those planets.
Exactly. So they thought Pluto was huge, but it just appeared faint because it was so far away. But as decades passed and our measurements got better, Pluto kept, shrinking in our estimate.
It's just getting smaller and smaller.
Right. Until by the 1970s, astronomers realized it was this tiny ice world, totally lacking the mass to have ever pulled on the gas giants in the first place.
And it wasn't just the mass, right? The orbit was completely bizarre.
Wow, the orbit is a mess.
Yeah. So, if you picture the solar system, most of the planets operate on a tidy, relatively flat plane. Think of, an old vinyl record spinning on a turntable.
Okay, good visual.
All the major planets, Earth, Mars, Jupiter, they're sitting neatly in the grooves of that flat record. But Pluto is completely ignoring the record.
It is entirely off the plane.
It's like a moth diving through the record at a steep, 17-degree angle?
Yeah, about 17 degrees.
And not only is it tilted, but its orbit is wildly stretched out. It's an oval. It's so lopsided that for a 20-year stretch of its 248-year orbit, Pluto actually dips inside the track of Neptune.
It does.
It sneaks closer to the sun than the eighth planet does. It doesn't sound like a stable, major planet. So I have to ask, were astronomers just ignoring these giant red flags for decades because they desperately wanted a complete set of 9 planets?
Well, what's fascinating here is that science often has to work with the best categories and the best technology it has at any given time.
Okay, fair.
In the mid-20th century, we just didn't have the technology to see anything else that far out.
Yeah.
So you have this object, right? It orbits the sun, it's round, it's far away. Based on the framework of the time, the only available box to put it in was planet.
It was the only label we had.
Exactly. It wasn't willful ignorance. It was simply the limitation of the era's technology. We categorized it with the information we had.
The universe just, hadn't shown us the rest of its cards yet.
Beautifully put, yeah.
Which brings us to the turning point. Because we stopped ignoring the red flags when our telescopes went through a massive technological revolution, right? We moved away from those glass photographic plates and started using CCDs, basically digital sensors, like highly advanced versions of the camera in your smartphone.
Yep, digital completely changed the game.
And these digital sensors revealed that Pluto was hiding a massive secret about the edges of our solar system.
Yeah, the technological leap in the late 1990s and early 2000s changes the entire map of the solar system. Astronomers start staring deeply into that same distant freezing region where Pluto lives.
Right.
And they realize Pluto is not alone out there, not even close.
Not by a long shot.
No. It turns out Pluto is just one piece of a vast donut-shaped ring of icy bodies stretching far beyond Neptune. We now call this the Kuiper Belt.
And for those of you listening, if you want a mental picture, think of the Kuiper Belt as a second, vastly larger asteroid belt.
That's a great way to think of it.
Right, because we have the main asteroid belt between Mars and Jupiter, which is mostly rock and metal because it's closer to the warmth of the sun. But the Kuiper Belt is much further out in the deep freeze of space.
It is incredibly cold out there.
Yeah, so the debris out there is mostly made of ice and frozen gases, not rock.
Exactly. And when the solar system formed 4.5 billion years ago from this swirling disk of gas and dust, the planets swept up most of the material.
Right.
But at the very fringes, the material was too sparse and too cold to clump together into a massive planet. It just stayed as a vast debris field of primordial ice. It's essentially a cosmic time capsule.
Oh, wow, a time capsule.
Well, and as our digital telescopes pierced the darkness of this region, we found countless objects. Everything from tiny chunks of ice to, substantial little worlds.
And the realization slowly dawns on the astronomical community. Pluto wasn't the lonely 9th planet bringing up the rear of the solar system.
Not at all.
It was just one of the larger members of this massive frozen crowd.
Yeah.
Which brings us right back to our stray cat analogy.
Yes, the cats.
You let Pluto in the house, but now you have hundreds of icy cats on your lawn.
And the situation becomes critical in the 2000s because astronomers start finding Kuiper Belt objects that are roughly Pluto's size, worlds with names like Haumea and Makemake.
Right.
But the absolute clincher came in 2005 with the discovery of a world named Eris.
Okay, I want to pause on Eris for a second, because if it was as big as Pluto, why did it take until 2005 to find it? Shouldn't we have seen it earlier?
That is an excellent question. Eris was incredibly hard to find for 2 main reasons. First, it is located in what we call the scattered disk, which is much further out than Pluto.
Okay, so it's darker.
Exactly. It reflects way less sunlight, and it moves agonizingly slowly across the sky. Remember Tomball's blink comparator.
Yeah, looking for the jump.
Right. You need an object to move noticeably against the background stars. But Eris is moving at a glacial pace. And second, its orbit is tilted even more crazily than Pluto's.
Wait, more than 17 degrees?
A massive 44-degree angle to the solar system's flat plane.
Oh, wow.
And since astronomers usually scan the flat plane where all the other planets are, Eris was just hiding way up in the attic of the solar system, where nobody was looking.
Okay, that makes sense. But once they finally spot it, they realize Eris is a total game changer. I mean, initial measurements actually made it look even bigger and heavier than Pluto.
Right. And if we connect this to the bigger picture, the discovery of Eris created a genuine structural dilemma for astronomy.
How so?
Well, if Pluto is a planet, then Eris, being practically the same size, absolutely must be a planet too.
Right.
And if those two are planets, what about Makemake? What about the next object you find? We could be looking at dozens, maybe hundreds of Pluto-sized ice balls waiting to be discovered in the Kuiper Belt.
So we really were staring down the barrel of having 50 or 100 planets. You'd have to update the textbooks every 6 months.
Yes. And kids would have to memorize a song with 100 planets in it.
That sounds like a nightmare.
It really does.
Yeah.
And scientifically, if you have 100 planets, including countless chunks of ice that are practically indistinguishable from one another, the word planet loses all scientific utility.
It just becomes a meaningless word.
Exactly. A category that lumps together a massive gas giant like Jupiter, which is hundreds of times heavier than Earth with 1,000 tiny icy rocks, doesn't actually help scientists describe the mechanics of the universe. The classification system was basically buckling under the weight of new data.
Which forces the scientific community to sit down and do something you'd think they would have done centuries ago.
You would think so, yeah.
Because the word planet was about to become totally meaningless, in 2006, the International Astronomical Union, the IAU, which is the official body that names things in space, they gathered in Prague to formally define what a planet actually is.
And it is genuinely surprising to realize that before 2006, science had no strict mathematical definition for a planet.
That is wild to me.
Right. It was just a historical assumption. You just kind of knew a planet when you saw it.
Yeah.
But Eris forced them to write rules. The IAU debated fiercely and ultimately settled on a 3-part definition.
Okay, let's walk through this definition because the mechanics of these rules are brilliant. The first 2 rules are pretty intuitive.
They are.
Rule 1, it must orbit the sun. So that immediately disqualifies all the moons orbiting Jupiter and Saturn. Pluto orbits the sun, so it passes Rule 1.
Right, easy pass.
Rule 2, it must be big enough that its own gravity has pulled it into a round shape.
And the scientific term for Rule 2 is hydrostatic equilibrium.
Hydrostatic equilibrium.
Yeah, it sounds complicated, but it's really just a battle between gravity and the structural strength of a material.
Okay.
If an asteroid is small, maybe a few miles across, the rock or ice is strong enough to hold a weird, lumpy potato shape.
Like a space potato.
Exactly, a space potato.
Mm.
Because its gravity is too weak to crush the rock. But if an object gathers enough mass, its gravity becomes overwhelming. The gravity pulls equally from the center in all directions, crushing the rock and ice until the whole world smooths out into a sphere.
Okay, and Pluto is definitely massive enough for its gravity to crush it into a sphere. So it achieves hydrostatic equilibrium.
It does.
It passes Rule 2 easily. It's 2 for 2. So far, we still have our 9th planet, but then we hit the trap. Rule 3.
Yes. The third rule is where the line in the sand is drawn. To be a true planet, a body must have cleared its neighborhood.
So what does this all mean? Cleared its neighborhood. I've always loved the mechanics of this concept. Let's use an everyday analogy.
Okay, let's hear it.
Imagine a true planet, like Earth or Jupiter, as a massive, heavy-duty snowplow driving down a street.
Okay.
The street represents the planet's orbit around the sun. A true planet is so massively heavy, and its gravitational dominance is so overwhelming that over billions of years, it sweeps up or violently flings away all the other loose debris in its path.
Right, it pushes everything out of the way.
Exactly. The street is completely clear behind the snowplow. But Pluto is just a regular car trundling along through a heavy snowstorm. It's driving right in the middle of a massive swarm of other cars.
That analogy gets right to the physics of the IAU decision. They use something called a planetary discriminant, which is essentially a math equation. They compare the mass of a planet to the total mass of all the other debris sharing its orbit.
Okay.
Earth is over 1 million times heavier than all the stray asteroids in its path combined.
1 million times.
Over 1 million, yeah. It is the undisputed gravitational bully of its neighborhood. Pluto, on the other hand, is only a fraction of the weight of all the other icy bodies swarming around in the Kuiper Belt.
It isn't the driver, it's just the passenger in the swarm. It hasn't cleared the street at all.
Exactly why Pluto fails the third test. It is not gravitationally dominant enough to have tidied up its own patch of space. Because of this, the IAU had to create a brand new category for worlds that pass the first two rules but fail the third.
And that's how Pluto was reclassified as a dwarf planet.
Exactly.
And it's so important to reiterate that this wasn't a punishment. Like, nobody was mad at Pluto.
No, not at all.
It was a necessary reorganization of our cosmic filing cabinet. We learned more about how the solar system formed, we recognized the Kuiper Belt, so we just needed better folders to organize the information based on how gravity actually operates out there.
Right.
But if you think the debate ended neatly in 2006 with everyone shaking hands and agreeing, you would be very wrong.
Oh, very wrong. This remains a genuinely contentious debate among many serious scientists today, because a lot of critics, especially planetary geologists, argue that the cleared its neighborhood rule is fundamentally flawed.
Right, because Rule 3 relies on orbital dynamics, like where a world is and what's around it. But geologists care about what a world is. And here's where it gets really interesting. Just as everyone is furiously debating this new dwarf planet label in the late 2000s, humanity decides to actually go there and look at it.
Yes, finally.
In 2015, a NASA spacecraft called New Horizons finally reaches Pluto.
And the scale of the New Horizons mission is just a triumph of engineering.
It's incredible.
It was the fastest spacecraft ever launched at the time. It flew for 9.5 years, utilizing gravity assist from Jupiter just to pick up enough speed to cross the 3 billion kilometers to the Kuiper Belt.
3 billion kilometers.
Yeah. And it didn't even have enough fuel to slow down and orbit Pluto. It had to execute a flawless, high-speed flyby, snapping as many pictures as possible in a matter of hours.
The tension must have been unbearable, because before 2015, our best pictures of Pluto, even using the Hubble Space Telescope, were just fuzzy, pixelated blobs.
Yeah, you could barely see anything.
Right, so people assumed a tiny dwarf planet 3 billion kilometers away from the warmth of the sun would just be a dead, heavily cratered lump of ice, just a frozen graveyard.
That was the expectation, yeah.
And then the high-definition images start downloading to Earth.
The imagery astonished everybody.
Yeah.
It completely rewrote our understanding of the outer solar system.
What did they see?
Well, New Horizons revealed towering mountains that rival the Rockies.
Mountains on Pluto.
Yes. And because the surface temperature is around minus 380 degrees Fahrenheit, the water ice making up those mountains is frozen so solid it acts like bedrock. It is as hard as granite.
That is wild. And surrounded by those mountains of water ice, they found this vast, perfectly smooth plain, famously shaped like a giant heart.
The famous Pluto heart, yeah.
And this plain is made of frozen nitrogen. But here's the crazy part. Nitrogen has a lower freezing point than water. So even at minus 380 degrees, the nitrogen ice remains pliable.
Right, it's softer.
Yeah, it acts like a slow-moving glacier. The images showed this nitrogen heart is slowly churning, bubbling up from below, erasing all the craters on the surface and renewing itself. Pluto even has a thin, hazy blue atmosphere.
And that geological activity is what truly shocked the scientific community. To see churning nitrogen plains in an atmosphere on a world that distant means Pluto is geologically alive.
But wait, how is that mechanically possible? We just established it's freezing out there. It's tiny, so shouldn't it have lost all its internal heat billions of years ago?
That is the mystery that makes Pluto so spectacular. The prevailing theory is that deep inside Pluto there is a rocky core containing trace amounts of radioactive elements.
Oh, interesting.
Yeah, things like uranium or thorium left over from the birth of the solar system. As those elements decay over billions of years, they release a tiny, steady amount of heat.
Okay.
And because Pluto is wrapped in a thick blanket of ice, that heat is trapped inside, like a cosmic heating pad.
So that trapped internal heat is slowly driving convection currents, pushing the slushy nitrogen ice up to the surface to create those churning plains.
Exactly.
I read there are even theories that this radioactive heating might maintain a liquid water ocean deep beneath the ice crust.
There are. Which brings the debate right back to the forefront. The planetary geologists look at the New Horizons data. The mountains, the glaciers, the complex atmosphere, the potential subsurface oceans, and they argue this world is incredibly complex.
I mean, I have to push back on the IAU's strict rules based on this too, because if a world has churning plains, geological heat, and weather, doesn't it fundamentally feel more like a planet than just a piece of icy rubble?
It certainly feels that way.
Right. Like, doesn't the sheer complexity of Pluto make that third rule about clearing its neighborhood seem a bit arbitrary?
Well, this raises an important question about how we classify nature. The geologists argue that a planet should be defined by its intrinsic properties, its geophysics. Does it have geology? Does it have a complex surface?
Right.
But the orbital dynamicists, who champion the IAU definition, they argue that a planet must be defined by its context in the solar system. Does it dominate its environment gravitationally?
It's a clash of perspectives.
Exactly. And this disagreement is an example of healthy science at work. As our sources point out, these scientific definitions are often more about usefulness than about uncovering some absolute universal truth.
Usefulness, let's dig into that,
Okay.
because the label dwarf planet is useful for an astrophysicist plotting the architecture of the solar system.
Yes.
It immediately tells them about Pluto's location and gravitational context within a belt of thousands of other objects. But dwarf planet doesn't mean it's a boring rock.
No, not at all. To understand the architecture of our solar system, we need to acknowledge that the inner region is dominated by rocky worlds, the middle is dominated by gas giants, and the outer fringe is a vast swarm of icy bodies.
Right.
Putting Pluto in the dwarf planet category alongside Eris and Makemake helps us understand that third zone. We completely reframe the narrative when we see this. Pluto wasn't demoted because it shrank or because it failed. It was reclassified because we realized it had a lot of company.
It's far better understood as the shining king of the Kuiper Belt than as the bizarre, mismatched runt of the major planets.
Yeah.
Pluto didn't lose anything in 2006. It gained a whole kingdom.
It is a profound shift in perspective. Science isn't just about preserving the models we learned in childhood. It's about remaining open to the unknown.
Yeah.
The story of Pluto's reclassification is a reminder that our mental maps of reality must always bow to reality itself, no matter how much nostalgia we hold for the old maps.
So for you listening to this deep dive, why should you care about the shifting labels of a distant ball of ice? Because this story equips you with a much better answer the next time you hear someone complain about Pluto's demotion.
Right.
You can explain the mechanics of hydrostatic equilibrium or the vastness of the Kuiper Belt. You can tell them about the mountains of rock-hard water ice, the trapped radioactive heat, and the churning nitrogen heart.
It's just a fascinating world.
It really is. Pluto is the